Here's an answer for question 5 from the week 3 quiz. So we're presented with the hypotheses that have been used in a hypothesis test. There's the null hypothesis H0, which is that the population mean is equal to 1, and then as our alternative hypothesis H1, we have that the population mean is not equal to 1. And the first question asks, how can you tell that this is a two-tailed test? Well, the answer is by looking at the alternative hypothesis H1, and specifically that it includes the not equals sign. What this is saying is if the null hypothesis is not correct, then it could be that the true population mean is above 1 or below 1. The above or below are effectively the two tails. If this had been a one-tailed test, then our H1, the alternative hypothesis, would have been in one direction only. We would have either said that if the null hypothesis is not correct, our alternative hypothesis is that the true population mean is less than 1, or we could have had it that the true population mean was greater than 1. This would have been a left tailed test, and this would have been a right tailed test. B, we're given the t-distribution that's being used in a hypothesis test and asked what conclusion will be reached on the basis of this t-distribution and also how you get there. So on the graph we're given the critical value for this test and the opposite of the critical value. You need both of those if it's a two-tailed test. If it was one-tailed, your critical value would either be up here somewhere or down here. You wouldn't have both. And the other bit of information that we're given is the test statistic, which is lurking down here to the left or below the negative TC. Now the conclusion that we will reach for this test is going to be that we will reject H0. These critical values set up a rejection region, which is the values above TC and below negative TC. So this is the rejection region, or half of the rejection region, and this is the other half for the two-tailed test. We have set these critical values by saying that if the null hypothesis were true, it would be very unlikely that we would see values of the test statistic out in these rejection regions. And in fact, if we did, then it would lead us to believe that the null hypothesis probably wasn't true. Now you can see that the test statistic here is actually in the rejection region. It's less than negative TC, and that's the reason why we're rejecting H0. So to explain how we reach the conclusion, we'll say that the test stat is in the rejection region, being less than negative TC. And underlying that is the idea that if the null hypothesis were true, there would be a very low chance that we would see a test statistic out in this range, and therefore it seems as though the null hypothesis is probably not true. For C, it says identify the two most important determinants of the critical values used for this two-tailed test. So critical values, TC, are based on three main things. One is going to be the significance level of the test. One is going to be, or another is going to be the degrees of freedom for the distribution that we're using for the test. And the other thing is going to be the number of tails. And in fact, it's probably, we could say more generally, it's the form of the alternative hypothesis, which tells us whether it's a two-tailed or a one-tailed test, and also for the one-tailed test whether we're doing a left-tailed test or a right-tailed test. So I've said a number of tails here, but in the case of a one-tailed test, it also matters whether we are doing a left-tailed test or a right-tailed test. Okay, in this case, the question is already saying we're doing a two-tailed test, so no marks for that. But our answer will be the significance level for the test, alpha. This is basically the chances of us falsely rejecting H0. Falsely rejecting means rejecting it when it's actually true. This will usually be set to a fairly low level like 0.01, 0.05, 0.1, and this is the probability that will be left out in the tails, so beyond the critical values. And the second main thing is going to be the degrees of freedom. This actually determines the precise shape of the t-distribution that we're looking at. The higher the degrees of freedom, the smaller the tails tend to be, and the more peaked it tends to be up here. So if I was to use more degrees of freedom here, I'd get something that looked a little bit more like this. So the degrees of freedom, df, determines the precise shape of the t-distribution that we're looking at, and that itself is equal to the sample size minus 1. So if you had said sample size, that would have been an acceptable alternative to the degrees of freedom. And the final question is to shade the p-value for this test. So we'll go back up to the graph of the distribution. The p-value is related to the test statistic, and it's in fact this area here plus the equivalent area, or a symmetrical kind of area on the right hand side, so here. So for a two-tailed test, the p-value is the area, or the probability, the area represents a probability of getting less than our test statistic, given that we're in the left tail, and then because it's a two-tailed test, you have to double that by setting up a corresponding region in the right-hand tail. And that's a brief answer to question 5.